How do solar panels work? Well, nuclear chemical reactions taking place in the sun release energy in the form of photons, electromagnetic packets of energy that spend 8 minutes traveling through the vacuum of space-time and getting to our planet, providing us with the energy that plants use and in turn providing life to exist. Solar cells convert this light energy into electrical current. American inventor Charles Fritz made the first working solar cell in the hopes of competing with Thomas Edison's coal power stations. However, they were only 1% efficient. Today's commercial silicon cells are upwards of 18% efficient and broadly available. Solar panels are composed of smaller units, solar cells. They consist of 2 layers of silicon, an N-type layer, silicon doped with phosphorus, which contain electron holes waiting to be occupied by electrons. A P-type layer, silicon layer, is doped with boron or gallium, which have extra electrons in their orbitals. Now, when a photon with enough energy strikes a P-type electron, it transfers its energy, which allows the electron to jump to the N-type layer, a free hole. This causes a potential difference and hence current will begin to flow. Solar panels consist of cells which make solar wafers, of which then construct the entire panel. The 3 types of panels you should be aware of are the following. Polycrystalline, which are the most affordable and abundant, like this over here. Monocrystalline, which are the most efficient and effective in cloudy and shady weather. And then there is thin film, which is lightweight and less efficient. So mono is the way to go if you can afford to do so. Panel sizes. Panels come in various power ratings, from 10 watts all the way to 750 watts, and they can be connected in series or parallel to your inverter. The string size will be determined by your inverter's maximum voltage and amperage of the panel DC input. It is recommended to only use one size of panel in your panel arrays. What affects the power output of a panel? Well, power equals voltage times current. So what affects voltage and current? 1. Azimuth. Which directions are the panels facing? North, south, east or west? The best direction towards is towards north in the southern hemisphere and south in the northern hemisphere. You can get away with eastwards or westwards, but then you will only be getting solar energy towards the beginning or the end of the day. Number 2, the elevation angle. This is the angle at which your panels are tilted towards the sun. Anywhere between 25 and 35 degrees will work here in South Africa. This angle varies depending on your longitude. 3. Shade. A splash of shade will affect the entire array since the cells are in series, so try and avoid shade at all costs. 4. Irradiation strength. The stronger the sunlight, the more current that flows, and this is measured in watts per meter square. Cell temperature. As temperature increases, your voltage will decrease. We work at a maximum ambient temperature of 60 degrees usually and a low of negative 10 degrees. The electrical characteristics of each panel. Now, most electrical characteristics are provided at standard testing conditions. That's 1000 watts per meter square, 25 degrees Celsius and 1.5 atmospheres. These are the electrical characteristics we look at. The maximum power, the open circuit voltage or VOC, the VOC coefficient depending on the temperature, the short current coefficient also determined by the temperature, and the efficient of transferring from watts per meter squared received versus the output current. So panels are generally connected using what's known as MC4s, and you get a male MC4 which has a female lug inside and a female MC4 which has a male inside. And it's simple. It's as simple as just plugging in and hearing a nice lovely click. Fuse protection. To size your fuses for a single string, obtain the short circuit current with the temperature coefficient in mind and times this by 25%. For a parallel string, add the number of parallel strings and times that by 25%. Safety. Now, it's always important to try and carry a panel between 2 people. When working on high-rise buildings, please bear your safety in mind. More people die in solar work than in nuclear energy because of this very reason. Wear steel-tipped shoes if you can, and rubber gloves that will give you extra grip. Grounding. Now, it's important to ground panels in a lightning-prone area and to install surge protection devices like this, so that when the potential difference of the panel is above a threshold, that this will trip and your panel won't. It'll protect all of the circuitry within your house. Now, one can earth the panel with a 6mm grounding cable like this directly to the distribution board, or another method of earthing your panels is by using an earth rod, which you will then use a 10mm cable, which you will then clamp to this part of the earth rod and hit this nicely into the ground. You also need an isolation switch, and this is to just isolate the panels from the inverter in case you need to work anywhere in the inverter. Alright, so that's more or less an introduction to the solar panels aspect of solar energy, the most critical part, I suppose, of the entire project. Now let's move on to the other DC component, which is your batteries.